Greetings everyone, this is non-expert here, back again with another video. Today we'll be solving problem number 33 and the difficulty has been rated at is easy. This problem was asked by Microsoft and let's just get down to the problem description. So the problem description is that we need to compute the running median of a sequence of numbers. That is, given a stream of numbers, print out the median of the list so far on each new element. So recall that the median of an even number list is the average of the two middle numbers. Alright, cool. So basically what the problem is that you're given a data stream of numbers, and as you're getting each number, you need to compute what's the median of that entire list that you sort of generated so far. Again, if you don't know what a median is, it's basically like if you have a solid array, what's the middle element if the length is an odd number, but if the length is even, then whatever is the average between the two middle numbers, that's your median. So as depicted in this example, if you're given the sequence 2, 1, 5, 7, 2, 0, 5, as you can see, if you sort of push in 2, what's going to happen is that you're going to get 2 over here. If you have 1, the array will become 1 comma 2, and since it becomes 1 comma 2, it still does not matter because the length is 2, so you compute the average between 1 and 2, and that's 1.5. Then when you sort of push in 5 to your sorted list, the array you represented would be 1, 2, and 5, but since this is an odd length array, you'll just pick out 2, and just because that's the middle element, and just print it out, and that's how it's sorted from there. So fortunately, we were able to find a similar problem on lead code, and let's just go there. So the name of the problem is find median from data stream. Again, this is sort of rated as a hard problem, and the reason why this is a hard problem is because there are a few restrictions which they've posed. They want you to sort of work on the most with the best complexity in mind. Whereas in the daily coding problem, there are no restrictions have been put. So basically what you could have done is you could just, as you keep on getting each element, you could just put it inside a solid array and, just compute from there. So the complexity of that would sort of be sort of like n square or something like that. But it's too heavy and we want to do something in a better way, right? So let's just get down to it. So the way to sort of handle this problem is by something called as a heap. If you don't know what a heap data structure is, it's a pretty common data structure and it's used a lot. So what we're going to have is we're going to have two heaps. So we are going to have a large heap and a small heap. And I'll explain what these heaps are. So basically a small heap is going to contain all the values um, which are lower bound. By lower bound, I mean from 0 to the middle element if they're sorted, like something like that, right? So everything which is in lower bound is going to go to a small heap, and this thing is actually going to work like a max heap, right? And that's something which you need to take care of. And I'll explain why it's a max heap as well in a moment. And the large is going to basically be the upper bound, and it's going to use the data structure of a min heap. Cool. So I'll get to the interesting part of how we can do this. So let's just write a few comments. So let's say that you have a list like 1 comma 2 comma 3 comma 4 comma 5, right? And let's just make small. Again, small is our our max heap, and our large is our min heap. So what's going to happen is as you keep on getting each element, you need to first understand how a small and a large would work, right? But before we do that, let's just set a rule. So the rule which you're going to set is that the two heaps which we have, the large heap or the small heap, when we sort of differentiate it, they should never have, never ever have a length difference of more than 2, right? So if it's 1, that's fine. But if it's 2, that's something that we need to sort of take care of, right? And since this is going to contain, or the small is going to contain the upper bound values, sorry, the lower bound values, and large is going to contain the upper bound values. Basically, if the length so far that we've sort of encountered, if the length is even, all we have to do is, pop out the first element from small and the first element from large. So what that would do is, it will give us the maximum element that we have in our lower bound, which is basically mid minus 1 or something like that. And large is, since it's a min heap, if we do large of 0, it's going to give us the minimum value which we found in our upper bound values, and that's going to be the middle plus 2, and we just compute the average from there. And that's what we need to do if the length is even, and if it's not, then what we need to do is we just need to return large, the minimum value of large, right? So large is going to be a source of truth, and let's just have a look at how we can compute all these things. So let's say you have 1, 2, 3, 4, and 5. So the way our heap is going to get structured, and again I'm going to go through a more array representation rather than an actual heap representation, just because I need you to understand that you're using arrays for your implementation as well. So the way to sort of go about this is that the only property which is sort of useful for us right now is that small, the index 0 of small, is going to have the maximum value that it can have so far, right? So when it does that, the way we're going to go about it is Python does not really have a max heap concept as such. It does have a heapify function and works as a min heap. You cannot, to my knowledge, you cannot use it as, and you cannot write comparators to it, and sort of convert it to a max heap. So the way we will go about it is we'll just give the numbers which we're pushing inside negative, and as we're doing that, we'll just it'll get sorted as a min heap, and it'll go on from there. Cool. So let's just go about it one by one. So let's say you have element 1, it will get pushed to your uh, large heap. Then when you have 2, 2 will get pushed again. But what's going to happen is that the length is actually greater than 2, the difference of the length is greater than 2, in which case what we need to do is we need to pop out the value from large, right? Just pop it out and place it into small. And when we start placing it inside small, we need to put it as -1. So we do that, and this is the entire representation, right? Then when you have 3, 3 gets appended to large, it's fine. But when you put in 4, what's going to happen is that this guy is going to say, hey, our rule is sort of breaking up. And let me just write this rule, right? So difference can never be more than 2. So when this happens, what do you do? You pop out the value from large. You say, hey, whatever value is there in large, you just pop it out, and you sort of place it inside over here. And the way you sort of place it is by, you have to negate it out. And since this is a min heap, this will become -2 and -1. So all you've done is, you've just popped out to pushed it inside small, but while you're pushing it inside small, you're sort of negating it and just go forward from there. So that's like the entire approach. And obviously, I've taken 5 over here as an example. But let's just take 1 and 2. What happens when 1 and 2 come again? So what happens is, you push inside large again, right? So this thing will get appended. Since 1 is the smallest so far, it'll get appended over here, right? And all you're doing is, you check again for the rule, so rule is still satisfied. Um, and then what will happen is that you need to understand that it's not inside the large bound, right? In a way, if you sort of look at it, it's like if you sort of consider all of these guys one by one, so the entire array which we have so far is 1 comma 1 2 3 and 4, right? So for those reasons, you have to make sure that you're handling this case as well, that 1 needs to be over here and 2 needs to get either popped out or pushed in or something like that, right? So again, it gets a little tricky to understand, but that's basically it. So we need to handle that condition as well, and we need to make sure that we're not facing any problems due to it. Cool. So before we start, I think like the way we should start with this is by actually writing the find median function. Um, so we've already written quite a bit of code for it. So let's just do that real quick. So all we're going to say is if the length of small plus the length of self dot large, if it is divisible by 2, or yeah, actually if it's divisible by 2, then we need to, compute the two values. So we'll just say, hey, return self.large, the first value inside our max heap, minus self.small 0 divided by 2. So the reason why I'm doing minus over here is just because of the type conversion. So as you remember, cell.small is going to be a min heap, but all the values are going to be as negative. And that's like a hacky solution, but that's like the only solution that we can go with. um, yeah, so actually you can just, just write this thing instead, because we know for a fact that it will never be thing. So if these two guys are the same, then you return it like that. Else, all you have to do is return self.large inside large. Right. So the way we're going to go about this is by actually importing the heap queue library. So let's just do that. Let's just say, um, actually, let's do from import. Oops. uh, Import. Let's just import everything for now, right? Um, so again, there's not much that we've done here. But the one thing that we need to sort of take care of is that, the small and the large values need to be compared properly. And that's actually pretty simple to do, to be very honest with you, because the way you can sort of think about it is that either you're pushing a value inside small or you're popping out the value. So if we just push the value inside small before we sort of, push it inside large, and just, pop out the least value and just push it inside large, that should, just take care of our entire condition. Again, if you didn't understand it, let me just write it in code so it'll be easier for us to understand. So let's just do that. So the first check which we do is, hey, if the length of both the guys is the same, right? If it's the same, what we're going to do is we're going to push our num value inside large, right? That's basically what we want to do. But the way we're going to do that is that we're going to be smarter about it. So we're going to say self large, and this is the way you usually do a heap push. But the way we're going to go about this is that the before pushing it inside large, we're going to push it inside the small heap. And what that would do is whenever I pop out the maximum value or whatever value that I have and negate it, I'm going to get out the minimum value or the largest upper bound value which we found so far. So if you have, let's say, let's just take this example. So when we have 3, 4, and so on, we have pushed -1 inside first, right? Then we pop out -2, right? Update its negative, whatever sign, and push it inside large. So that's how we're going to go about it, and we're going to use something called as a heap push pop. Again, if you don't know what it is, it's a pretty simple structure which just states that, hey, I'm going to first push inside this value, and then I'm going to pop out the value which is there. We need to make sure this is negative, and that's basically it. Again, if you didn't understand what this is, we're basically saying that before pushing inside the large heap, right, uh, we need to make sure that we push it inside small so that we get the value, we get the first value, which is the more important value for us. This just sort of helps us prevent a lot of if conditions, and you're obviously going to save that value as a negative value because the small is actually being represented as a max heap. And while you're doing that, you do num, and whenever you pop it out, the pop is going to always, the heap pop, the way it works is it just pops out the first element. So it's going to pop out the largest value or whatever that you want to call it, -2. Um, and it's just going to, return it back to self large, and that thing is going to get pushed inside your heap push. Again, it's a little tricky to understand what's happening here, so I would like, suggest that you pause this video and try to write it down on your own. But it's pretty simple, to be very honest with you. Again, so we've handled the case when both the values are equal, when both the lengths are equal. Now what we need to do is we need to handle what happens when large is sort of greater or so on. And the idea over there is also like the same only. Like the heap push is going to go on self.small, but before you do that, you do a heap push pop on self.large and just provide it with the num value. And since we want it to be a negative value, that's what we're going to take care of, and that's basically it. So we sort of not use a lot of if conditions. If you're comfortable with those if conditions, checking for whether you need to where you want to push that value inside, either you want to push inside small or large, that's on you. It's okay, I completely understand. But this is also one way of going about it. I like this approach a lot more because it's pretty small, and you're using the same approach over and over again. Again, the heap push pop is actually much more faster than you're doing a heap pop and then a push. So that's the main reason why we're sort of using that approach. Yeah, so again, if you do not understand what this is doing, we can go with a more simpler route as well. And I'll just write the simple solution as well. So the simple solution is just going to be that you check for whether um, what's the value of what's the peak value at small. I just try to understand whether I need to add it inside small or whether I need to add it inside the higher value, right? So let's just get down to it. So you basically say that hey, if self.lower exists, basically if something is there, uh, or rather, let's just say hey, if self.large, if it exists or if it does not exist. So basically, if not self.large, or let's just say um, self.large 0 is actually less than, or rather, oh no, actually it's less than. So if it's less than whatever is the num which has been given so far, then we sort um, we don't push it inside that value. We try to go one above, right? Or another way you can sort of think about this is that you say that hey, if sorry, um, if the number is way greater than the minimum element that we found so far, then we know for a fact that hey, this thing needs to get appended. So the way we can do that is just right heap push self dot large, and we give the num, right? Um, Otherwise, you sort of push it inside the other one. So you say hey, push it inside small, and we're gonna push in minus num. And then what you want to do is you want to make sure that you're rebalancing it out in a perfect way. And by rebalancing, what I mean is that you want to understand that hey, either the top value of self large needs to get pushed inside self small, or the other way around. So you can do that. You can just have to say that hey, if self dot large um minus length of self dot small, if it's greater than 2, basically you're not, or sort of greater than 1, because you want to consider 2 as well, in which case what you want to do is you want to push inside, sorry, push self small, basically inside the small heap. What you want to push is you want to push in the top value of self dot large. So you want to do a heap pop self dot large, and that's it. So it's going to return the highest value which is found so far, and then push it inside self dot small from there. Again, pretty simple. But I like the other approach better because you don't have to really worry about rebalancing it, and it's just more efficient approach. But again, I sort of like the other approach much better because you don't, there's a lot more if else conditions which you'll keep on pushing inside this thing, and this is a more efficient approach as well. So that's basically it. Now let's just try running this once. But before we do that, uh, I would urge you to write it down. Just check out whether everything is working fine or not, because I believe that can get a little bit complicated to understand what you're doing. Uh, but all in all, it's a pretty simple approach. All right, let's just try running this code. Hopefully, it should run. We are getting an error. Oh, okay. Yeah, maybe just converting it to a float, something which is required. Yeah, cool. So it seems to be running fine. Let's just try submitting it. Hopefully, it should get submitted. And awesome. So it is working fine. As you can see, it's performing well as well. All right, so that's it for today's video. It was a pretty long video, but I believe I've like explaining it short took a lot of time. But all in all, it's a pretty simple approach if you sort of think about it. All right, if you did have some comments, do leave it in the comments below. And if you did like this video, do give a like and do subscribe to this channel. We are a discussion over here, and we'd love to have you on board with us. Again, if you've already subscribed, you're awesome. We all know it, and have a great day. Thank you.